In this video I'll be doing the coin change problem. That's the question of given coins of a certain denomination, here 1, 5, and 6, what is the minimum number of coins needed to add up to a target value? Here we're using 10, and I'm doing this problem as part of a series on dynamic programming, and I've been introducing the problems in order of increasing difficulty. So if you're having trouble with this problem, you might want to go back and check out some of the previous problems I've done. The first thing to point out about this problem is that the greedy approach doesn't work. So by greedy approach I mean simply taking the largest coin that you could possibly take for a given target and then just applying that process over again until you reach the target. And so for this problem that would be taking 6, because that's the largest coin, and then the target would be reduced to 4, and then 6 would be bigger than 4, so we would go to the next coin, and 5 still bigger than 4, and then we would ultimately end up taking 4 more ones, and that's 5 coins. And you can see that that's not the optimal solution because we could have just taken 2 5s. And so we're going to end up using a dynamic programming approach instead of the greedy approach for this problem. For the dynamic programming approach to the problem, we can think back to the staircase problem. And so we think about what the last step in this problem will be. And in a sense what we've been doing in this problem is we're taking coins and we're just adding up until we reach a target of 10. So at the last step we're either going to be taking a coin with a denomination of 6, of 5, or of 1. And then all we then have to do is subtract the target from whatever that value is. So we're going to make a recursive call. When we take the 6, we're going to change the target to 4. And we're going to make that recursive call, find the optimal solution for when the target's 4, and we're going to have to do the same thing for 5, so then the target's going to be 5, and for 1 the target's going to be 9. And so in code all we're going to have to do is loop through these coins, make the recursive call for what the remaining target is, and then we're going to add 1 to it, and we're just going to keep track of what the minimum is because we're trying to find the minimum number of coins. And then recursively in that recursive function, then all we have to do is take care of what the base case is, which is when the target is 0, you just need 0 coins. And if the target ends up being negative because you subtract off a larger value, then you just need to return some type of invalid value so that you can skip over that possible answer. And when you do that, you then have the top-down brute force solution. And then, just like in the previous problems, if we introduce caching, we then have a top-down dynamic programming solution. The last thing we're going to do is convert the top-down solution to the bottom-up solution. So for that, all we have to do is instantiate an array to save all the values of the subproblems, and that's going to be a length of the same length as the target. And what we're going to do is we're going to build up starting from the base case, which is for a target of 0, take 0 coins. And at each index, as we're building this up, we're going to loop through each of the coins, and we're going to subtract off that value to look at the previous target and the answer for that. And that'd be adding 1 to that value, because that'd be kind of like taking that 1 coin, and we just minimize over the possible values from each coin. And we just have to take care to ignore the invalid negative values. And so, for example, at this last value 10, we're just looking back over the sub-solutions for 9, so that's when the last coin's a 1, and for 5, so that's when we take a 5 as the last coin, and we have to look at the sub-problem of 4 for when we take the last coin of 6, and we just minimize over those values. And when you do this, you end up with a solution that's, I guess the space complexity or the space requirement is relative to the target, and then the time complexity is going to be the length of the coins times the target, because at each index as we build this up we have to loop through the number of coins. And so I'm going to do the implementation in the next video.